Now let's talk about SN1 reactions. As I said before, and this is going to sound a little repetitive, SN1 reactions go through a carbocation. So SN1 reactions, even though there's a 1 in the name, they go through two steps. The first step is the leaving group leaving the alkyl halide and then forming a carbocation. And then that carbocation gets attacked by the nucleophile. This reaction is unimolecular. What it means is that it's first order kinetics. And what that means is that the rate of the reaction is a K multiplied only by the substrate, because the substrate, it's the only species that determines the rate of the reaction. So if we go back to our example, this first step is going to take much more time than the second step of the nucleophile attacking the carbocation. That second step is very quick because we have a plus being attacked by a minus, and that happens very, very quickly. But the first step, where the carbocation has to form, the leaving group has to leave, that is the rate determining step. So that's why we only account for the concentration of the starting material in the rate. So this is a reminder of what we saw in chapter 6, where we were talking about energy diagrams. So here we have our starting material, and then it goes through an intermediate. The intermediate is the carbocation, and it gives us the product. In between each one of them, there is going to be a transition state, right? So we have two steps. That means two transition states. And now we can look at the activation energies. Remember, we have activation energy 1 and activation energy 2. The reason why the second activation energy is so small is because the reaction of the nucleophile attacking the carbocation is going to be very, very quick. So you barely have to put any energy for that to happen. And this one on the other side is going to be much lower. Remember, this is going to be the rate determining step, and so that's why that activation energy is very high. The other information, there's so much information you can get from this graph, but another one is, remember this one, this delta H is negative, and that is telling us that this reaction is going to be exothermic overall, right? Because if we look at separate steps like we did today in recitation, if I look at step 1, that step 1 is not going to be exothermic, it's going to be endothermic, meaning I have to put energy for that to happen, because the energy of my intermediate is higher than the energy of my starting material. So I have to put energy to get to that point. And then the difference between the product and the starting material, right, the product of that first step is going to be positive. But the second step, here I go from my intermediate into my product, and that second step, it's going to be exothermic. But then the other thing you can evaluate is comparing the starting material with the final product, right? So we can do it stepwise or overall, like we did today in recitation. And there are different ways of determining if one reaction is going to go through an SN1 or an SN2, but maybe the most obvious one is when we look at the configuration of the center where the reaction happens. Okay, let me explain that. As I mentioned in the previous video, the one in SN2 reactions, the consequence of having an SN2 reaction is that there's an inversion of the configuration at the center. But for an SN1 reaction, it goes through a carbocation. And carbocations are sp2 hybridized. And because they are sp2 hybridized, they become planar. Remember that sp2 carbons are trigonal planar. And because they are planar, when a nucleophile has to come and attack that center right there, it can either come from the top or it could come from the bottom right there. And so when we have an SN1 reaction, we could get two products. We'll get a mixture of the nucleophile attacking from the top and the nucleophile attacking from the bottom. And remember that these would be different stereoisomers, and stereoisomers are different. And this process is called racemization. Remember in the chapter where we talk about optical activity, we talk about racemates, and racemates being mixtures of 50-50 of the two isomers. So this is exactly how you get a racemic mixture, by an SN1 reaction. In an SN1 reaction, you see the Br leaves, and then we're going to get a carbocation. Now the nucleophile can attack from the top, giving us this product, or it could attack from the bottom, giving us the other product. And we will get a 50-50 mixture of both of them. And in SN2 reaction, the substrate matter when it comes to decide if the reaction was going to happen or not. Remember that for SN2 reactions, we were looking at substrates that were not hindered for the nucleophile to be able to go and attack. For SN1 reaction, the trend is actually the opposite. And the reason for that is because of the stability of the carbocation. I'll talk about it in the upcoming video, but carbocation stability increases as you increase the number of R's connected to the carbocation. So when we have a carbocation such as this one with hydrogens, that is a very, very unstable carbocation. But a carbocation that has 3 R's, let's say 3 methyls, for example, that is the most stable carbocation. So a reaction that starts with a tertiary alkyl halide always will go through an SN1 reaction. And a reaction that has a primary alkyl halide always will go through an SN2 reaction. But a reaction that has a secondary alkyl halide, it depends on the nucleophile, the solvent that you use for the reaction. So I'm going to say that one more time. A reaction that goes through a tertiary, that starts with a tertiary carbocation, will always go through an SN1 because that carbocation is very stable. But a reaction that goes through an alkyl halide that is primary is never going to go through an SN1 reaction because the carbocation that will form would be a primary carbocation, and that is a very unstable substrate. So let's summarize the SN1 reactions. So it's a first order reaction. That means that the rate only it's only determined by the alkyl halide. It happens in 2 steps. It goes through a trigonal planar carbocation, and that allows the racemization to happen. So that means getting a 50-50 mixture of the 2 possible stereoisomers. And for the R, the more substituted the carbocation is, the more stable